Thank you, Simon. Good day, everybody. Just to introduce myself again, my name is Denny Boysiboa, and I work for Mondi as a junior forest operations research specialist. Today, I'm going to talk about our journey to using harvesting machine data in forestry. The current journey to precision forestry to improve competitiveness through a productivity and efficiency step change requires us to have an in-depth understanding of big data and how can this be translated to information for data-driven decision-making. So cut-to-length harvesting machines have sensing technologies which collect data, and this can be interpreted to information through the application of advanced analytics to support decision-making in mechanized cut-to-length forest operations. So now the question is, what can we actually use harvesting machine data for? What we know so far is that machine data can be used to generate productivity reports for optimization and operational efficiency. It also provides us with an automated data collection for productivity modeling and for benchmarking operations. We also get stand information, which provides us with a full compartment enumeration, which in turn supports planning and aids in precision silviculture. So all of this information can be used to generate visualization tools for productivity heat maps and operational dashboards with productivity and stand characteristics. This in turn will lead to a data-driven real-time management system to improve operational planning, scenario and resource planning for other succeeding operations, thus creating a data-driven decision-making environment. So our machine data is divided into 5 phases. So for the first phase, we looked at the harvesting head capabilities. So here we wanted to clearly understand what is actually measured by the harvesting measuring system and what kind of softwares do you find on these harvesting systems and whether they are Stanford D compliant. And here we saw the Mondi parser being developed to be able to access the data. And then for phase 2, we looked at compartment level accuracy trials. Here we looked at the accuracy trial of the Warata harvesting head, and we also investigated how can we do productivity modeling with the harvesting machine data. For phase 3 was productivity heat maps. This involved GPS trials. So what we did is we installed a GPS device on harvesting heads, and then we had a GPS pilot trial. Here we wanted to test the suitability of the tracking device we installed on the harvesting head, and also we're focusing on machine data timestamp accuracy. For phase 4 will be our machine data strategy, where we want to develop a harvesting machine data strategy and implementation plan. And then for phase 5, later on, will be automation and database management systems. And then for phase X, this is more a collaborative effort with the Stellenbosch Machine Data Working Group, where we want to clearly understand, are we receiving an under and over back harvesting head measurement? And then we want to see whether 1, 3, or multiple passes actually have an influence on the harvesting measuring system. So with this project, we have adopted a culture of continuous improvement to constantly review our achieved outcomes, to highlight improvements, test new systems for data collection and data management techniques. So for this presentation this afternoon, we're only going to focus on phase 2 and phase 3. Meaning for phase 2 will be what when we investigated accuracy of the harvesting heads, when we model productivity from the harvesting head, comparing it with your manual time studies. And then for phase 3, where we looked at a suitable tracking device to mount on the excavator-based harvesting machine and the generation of productivity heat maps. When you investigate the relationship between data quality and cost of different data collection methods to model productivity of harvesting heads. Now, from image here, let's look at the differences in data collection and quality of harvesting head data compared to manual time studies. If you look at the machine data, it provides low data collection cost, but with a low data quality in terms of accuracy. And then on the other hand, with your manual time studies, it provides high data quality, but at a high data collection cost. If you look at the advantages of using harvesting machine data, is that it's cost effective, it's time efficient, and you get big data sets. However, there's uncertainty in terms of its data quality, and unplanned changes in working conditions cannot be seen. One other thing is that the work cycle time elements cannot be isolated, meaning you cannot like isolate your felling, your processing, and your debugging times. And then let's look at the manual time studies. So advantages here, it's got high data quality. You have skill observers on site. Work cycle time elements can be isolated, and it also accounts for unplanned working conditions. Disadvantages of this, it's time consuming, it comes at high data collection costs, and you also get small data set from spending long periods of time in the field. And again, you require skilled observers. You can't just send anybody to do time studies. They need to go to the proper training. So now let's look at phase 2, the machine data accuracy trial. Let's look at some of the background information. The trial took place in Zululand. We used 2 excavator-based harvesters. This was a one-pass processing operation, and the machines were calibrated for length. And it's pointing to say that the contractor does also calibrate these machines for diameter. So if you look at the site, this was a GXU compartment with an average tree volume of about 0.1 tubes. The harvesting head we used was a Warata H215E, and then the image on your far right will show you the Temerite software. This is what we use to create the production files and download them after the trial. Let's look at our methodology. So for this, we had 2 main objectives. The first objective was to look at the harvesting head accuracy by comparing machine data measurements with your manual measurements. And then the second objective was to compare productivity model from your machine data measurements with one from manual measurements. Let's look at the first objective. For this, we created a new production file on the harvesting machine, and then we had plots of 5 trees each. So once the trees were felled and were processed, we went in and did physical log measurements. Here we measured your small end diameter, large end diameter, length, and later determined our log volume. And then after this, we downloaded the STM file from the machine, and this was meshed with the manual plot measurements in terms of the SED, LED, length, and log volume. Then for the second objective, before the start of the trial, what we did is we created new production files on harvesting machine. And then throughout the duration of the trial, we did productivity plots. So a productivity plot had about 20 trees each. From this, we measured our DBH, we measured our height, and then we got our individual tree volume from our growth and yield equations. And then we did time studies during the manual measurements. And then after the trial was completed, we downloaded the STM files from the harvesters, and we're more focusing on your individual tree volume and timestamp. And both of these data collection methods, we modeled productivity and compared the results. The measurement accuracy. So how did we determine the measurement accuracy? We looked at something called measurement error. For this, we looked at the actual measurements will be your physical measurement on the ground, subtracted by what the machine is saying, meaning the machine measurement. So if your error measurement is greater than 0, meaning your machine is underestimating. And then if your error measurement is less than 0, it means your machine is overestimating. So we had to look for a standard that we can use to gauge our results. And then we use the measure up standard. This is SCOFO standard, where it states that proportion of measurement should fall within plus minus 4 millimeters for diameter and within plus minus 2 centimeters for log length. However, we could not find a standard to gauge for log volume. So we used our Mundi critical measure standard, which says that volume variations should be within plus minus 10%. So now if you look at the image on the right, we adapted this from Noston Hemerson. They published it in 2018. So here you're looking at an example of your measurement error for log diameter. So you have your actual measurements, millimeters, against your error measurement. So all your values on the 0 line, meaning there is no difference between your machine and your manual measurements. And everything within the range of 4 and -4 millimeters is regarded as acceptable, and all the points that are greater than 0, this is where your machine is underestimating, and all the points where it's less than 0, this is where your machine is overestimating. Let's look at the results for our harvesting head. We found that it's overestimating your lug length by about 25.4 centimeters on average, and that only 3% of the sample was within the acceptable standard of plus minus 2 centimeters. And then the machine was underestimating both your small end diameter and your large end diameter by about 6 and 7 millimeters on average, respectively. And only about 39% of our sample size was within the acceptable standard of plus minus 4 millimeters. Lastly, if we look at our log volume, the machine was underestimating it by about 19% on average, and only about 34% of our observations were within the accuracy standard of plus minus 10%. Let's have a look at the stats. Firstly, when we refer to log 1, we're basically saying the first log that was processed. So log 2 will be your second log, and log 3 will be third log. So during this trial, the machine was processing a maximum of 3 logs from one tree. So let's look at the length measurement error. We found log 1 and log 2 differed significantly from log 3, and then we found no significant differences between log 1 and log 2. From this, you can see that your first log has your highest measurement error and your lowest accuracy, while the third log, which is the last log that was processed, has your highest accuracy and your lowest measurement error compared to the other 2 logs. And then if you look at your small end diameter measurement error, we also found log 1 differed significantly from log 2 and log 3, and then we found no significant differences between log 2 and log 3. Similar finding with log length measurement error, whereby your first log process has the highest measurement error, lowest accuracy, and then the third log process having the highest accuracy. Lastly, let's look at the volume measurement error. Similar findings again. Log 1 differed significantly from log 2 and log 3, and no significant differences between log 2 and log 3. Again, the first log has the lowest accuracy, and then the third log from both length measurement error, small end measurement error having the highest accuracy and the lowest measurement error. Look at the findings. So for log diameter measurement accuracy, we found that the machine was underestimating our diameter. A finding by Sethforth in 2014, he found that diameter sensors on warrator heads tend to be calibrated to underestimate your diameter. So this is some of the factors some of a factor that we think had an influence in the harvesting head measurement accuracy for your log diameter. And then for log length measurement accuracy, we found that the machine was overestimating our length, and this could have purely been influenced by the operator. For example, when the operator is felling the tree and is about to process it until the harvesting heads, when they zero the guide bar, there is a gap between the butt end of the log and the guide bar. And thus, when the log is being processed, this results in overestimation of your log length. This was actually a similar finding by Steingart and Walsh in 2012, whereby they also found that restoring the guide bar when no contact is made between the log end also results in overestimation of your log length. And in 2014, Sethforth found that single pass processing to have higher length errors compared to multiple pass processing. So this is some of the factors that we might think could have had an influence in our harvesting heads measurement accuracy. So based on the results and the standard that we have used, our machine measurements did not meet the acceptable standard. And then the question is, then how can we improve the harvesting measuring system? By optimal machine settings per operating conditions, making sure you have your correct pressure settings on your machine, and making sure that your length and diameter sensors are in good working conditions. And it has been proven from time and time again that regular machine calibration does improve your harvesting measuring system, and that operator training will help to achieve high measurement accuracies. Let's look at our second objective, where we model productivity for manually measured data and harvesting machine data. For manual measured data, this is just the data we collected from all our physical tree measurements, including manual time studies. Our sample size here was about 842 observations. In terms of data cleaning, we followed our general time study protocol where we removed broken trees, dead or damaged trees. Then from the harvesting machine data side, our source was the consolidated STM files that we extracted from the harvesting head. Our sample size here was above 51,000 observations. In terms of data cleaning, we only considered trees that were harvested between, the time to harvest a tree was between 10 and 120 seconds, and with a utilized stem length, which is greater, equals to 2.6 meters. However, we omitted trees that were harvested at the time of delay. Let's look at the results. In terms of the harvesting machine data side, we removed about 9.8% of the observations. What you're looking at now, you're looking at a productivity curve model from both machine data and manual data plots. Here you're looking at the relationship between your tree volume in cubes and your productivity in cubes per productive machine hour. Both of these productivity models are significant at a 5% significant level. The blue trend line shows you the machine data curve with an R squared of about 60%. And then your black trend line will show you the curve of manually collected data with an R squared of about 67%. Then if you look from a tree volume of about 0.05 to about 0.015 cubes, there's not much difference between the two curves. And then if you're moving away from 0.15 to about 0.2 to about 0.25, you'll see there's a slight difference between the two curves. This was mainly because the data points for manual data points are grouped around 0.1 to 0.15, while the machine data points range from 0.05 to about 0.25 to 0.3. Let's look at the results for productivity modeling. So what we found is that we found significant differences in both tree volume and total time per tree for between machine data and time study data. However, when we model productivity, we found no significant differences in productivity between machine data and time study data. So here we took productivity models for both machine and manual data plots and estimated productivity at different tree volumes. So from 0.05 cubes to 0.3 cubes. And then we calculated the percentage difference between the models with the following equation. So what we said percentage difference will be manually measured productivity subtracted by machine data measured productivity divided by manually measured productivity times 100 to get a percentage. So you have your tree volume in cubes against your percentage difference. So what we found is that at a tree volume of 0.1 cubes, which was the average tree volume of the compartment, the differences between the projections from the models were just only 2%, meaning your machine data was overestimating the predicted productivity by only 2%. And then from 0.05 to about 0.013, you can see that the differences here in projections between the two data sets between the two curves was about less than 5%. And then from 0.14 to about 0.22, the differences were less than 10%. However, from tree volumes of 0.22 and going to 0.3, you can see the percentage differences are increasing from 11-12 to about -15%. So here meaning that your harvesting machine data will be overestimating the predicted productivity by 15%. Look at our findings. Machine measured data, we found that it's underestimating your stem volume by 4% based on percentage differences. And as we said before, the differences are significant. Again, overestimating your total cycle time per tree by 7%. Again, significant differences were found. And then on the productivity side, it was underestimating your productivity by only 2%. However, here we didn't find any significant differences. In terms of a machine data productivity model, we found that at tree volumes, less than 0.22 cubes, there was a variation less than 10% from the time study models. And then from tree volumes greater than 0.22 cubes, the variation was greater than 10% compared to your time study models. So now machine data productivity model accurately predicted our productivity only at the studied mean tree volume of 0.1 cubes. Now we're gonna dig into phase 3. Main purpose of this was to identify a GSM GNSS device capable of using GPS and GLONASS satellites for positioning and geospatial data collection and communication. So here we wanted to track and generate productivity or stand heat maps from excavator-based harvesters, which are Stanford D compliant. So we identified a tracking device, and which was the suitable tracking device that we identified was your GeoTap Geo9. This was connected on the OBD port of the harvesting head, which was fitted like into the excavator cab. If you look at the image on the right, you're looking at a Kobelco excavator with a Warata H215E harvesting head, and the arrow is just pointing at the position where the GPS device is fitted. The excavator has got a boom length of about 9 meters with an effective reach of 7.5 meters on average. So what do we get from the tracking device? We're currently receiving geospatial coordinates with timestamp. We also have a PTO function, which is mainly a push to operate function, and the data can also be pulled online at any time. We get daily reports on machine productivity, and based on the knowledge from our GIS team, the GPS device is its accuracy is acceptable. However, we are experiencing a number of challenges. Firstly, is that the tracking device it's fitted on the excavator cab rather than on the harvesting head. So we are not getting a GPS device for each individual tree. Second challenge is that the machine data still has to be physically pulled from the excavator-based harvester, and we're struggling a bit with the timestamp accuracy on the onboard computer systems. This happens when the machine is being isolated or it has been stopped for a long period of time. With assistance from our GIS team, they did a hotspot analysis using stem volume for one harvesting machine moving through a number of compartments in just over 4 weeks with a sample size of approximately 35,000 trees. So if you look at the legend, your blue values or your lighter colors will be a dense cluster of low values. This will be where you're having a lower stem volume, and then your red colors, your slightly darker colors, this will be a dense cluster of high values. This is the area where you're looking at a point whereby you have a higher stem volume. So if you're looking at point A, you can see there's a dense cluster of high values. So meaning at that compartment, your stem volume was higher. And then if you look at point B, there's an edge line. You can see the machine move on the edge line, and you can see the effect of the bigger trees because you have a dense cluster of high values. Again, on point C, you can see the effect of the edge line where the machine has moved compared to the other patches. And then on point D, you see a lot of blue colors from that point. This just shows you the dense cluster of low values where your stem volume was slightly lower or smaller. And then on point E, you can see that you've got a majority, if you've got a dense cluster of high values where your stem volume is higher. However, you have a patch in about the middle of the compartment where you have a dense cluster of low value. So you see a bit of variation from that compartment in terms of the stem volume. Now we're looking at a hotspot analysis again, but now we're looking at the cycle time per tree. So here your dense cluster of low values will be points whereby you have low cycle times, and where you have a dense cluster of high values, you're looking at the point whereby you have longer or more cycle times to process a tree. Let's look again at point A. You can see it's slightly similar to what we saw from a dense cluster of high values in terms of stem volume, whereby you still have a patch of a dense cluster of high values. This just shows you that the bigger trees take more time to be processed, so that's why we have higher cycle times. Again, at point B and point C, we do see a cluster of bit of high values where you have higher cycle times influenced by the bigger trees on your edge lines. And then on point D, again, you can see that where we had a low cluster of values in terms of your stem volume, you can slightly see its influence on your cycle time per tree, whereby you have slightly smaller processing, quicker processing times compared to point A. And then on point D, on point E, you can see that on this part where for stem volume you had a high cluster of high values where you had a higher stem volume. You can also see here how it influenced your cycle time, whereby you had higher cycle times. And then on the patch on the middle of the compartment where you had a dense cluster of low values where your stem volume was slightly lower, this is the point whereby you're having lower cycle times because you have a dense cluster of low values. So in summary, although it's early days for us with this machine data project, our results have highlighted a huge potential to drive decision making with harvesting machine data. And for us to be able to meet the strategic objectives that we have outlined before in the presentation is that we need to clearly understand the accuracy of the data we're getting from the heads, and that we have to be able to validate the quality of the data we get to avoid making decisions from poor data quality. And lastly is that to clearly define data visualization tools and the outputs that we're going to use. So what's next for us? For phase one, we're gonna continue with identifying harvesting heads for possible data collection. And then we're gonna look at the tech for effect green box so that we can start automating our data collection process. For phase two, we're gonna continue with our compartment level accuracy tasks. And for this day, we're gonna focus mainly on phase three, where we're gonna be looking at GPS device compartment level ties so we can get productivity heat maps and we can start visualizing the stand attributes that can help in precision silviculture, and then just brush up our machine data strategy in terms of our machine data collection standard, our harvesting machine data calibration standard, and later look at automation and database management systems. Just to acknowledge everyone who's been involved in the project so far, the SQF harvesting team, Sarisa Hlati, the harvesting contractor, for letting us use their machines, Gareth Bell from Bell Equipment, Charles Watt, our consultant, Carl Batista, who developed the Mondi Passer, Miranda Wilson, who has helped us in terms of generating productivity heat maps, and all other Mondi personnel who have been involved in the project. Thank you.